Hi everyone. This video is about the applications of polynomial functions. And since it's about applications, we can't possibly cover every example of an application. We're just going to focus on volume today. And think about why volume is an appropriate application of a polynomial function. Volume is 3 dimensions, right? And each of those dimensions you could think of as a degree, which would become a cubic function. So that's exactly why we cover this during polynomial functions. So let's get into a specific example. So let's say we have a flat rectangular piece of cardboard, but we want to fold it up into a box that would have volume. We would do that by cutting out a corner from each of the original corners of that piece of cardboard. So let's say here that we have an X inch by X inch square, right? And we're going to cut that out so it's no longer attached to the piece of cardboard. We would want to do that on all 4 corners so that we have the 4 sides, right, that we could fold up. So we have some dimensions now of this piece of cardboard, right? That would then fold up into this picture that I've put up here on the screen. We got that by folding along these yellow dotted lines. If we did that folding, it would create a 3D shape. If we make bigger squares, we're going to have a taller and taller box, right? But the base of that box is going to keep getting smaller, right? And you can see that from these 3 different examples. So, like I said, we're going to work with a real example here. Let's go right to it. So our first question, what is the maximum volume achievable from an 8-inch by 11-inch piece of cardboard with X inch square corners removed and folded into a rectangular prism? So we have this diagram now with some more specific dimensions. This entire side here was 8 inches. And this side was 11. But remember, we cut this square out of every corner. So we actually need to label some more dimensions on the screen. So let's get right to it. We need to know what this side here is. That's the 11-inch side, but this piece here was cut off, and this piece here was cut off. And both of those pieces were X inches long, so really that's 11 minus 2x, because we cut 2 of the x's off. And then this side here originally was 8 inches long, but just like with the other side, we took an x here and an x here, so this is really 8 minus 2x. All right, so now let's think of volume. To think of volume, we're going to need to think of this 3D figure. So I'm just going to draw this box in 3D again. And I'm going to label what each of the dimensions are. So the length would be the 11 minus 2x. The width here would be the 8 minus 2x. And the height of the box we get from whatever this x is, right? That's creating the height. So we'll label that x. So the volume is the length times the width times the height. I like to put the height in front over here. So we need to find the maximum volume. Well, to find the maximum volume, if I don't know calculus, I'm going to need to use a calculator to determine that. So I'm going to switch over to a graph on Desmos. I would recommend that you graph this on your graphing calculator and find an appropriate window. And we are looking at a cubic function, like I said before. But we're looking for the max volume, and you'll notice that the end behavior of this, right, the end is going to infinity. But really that doesn't make any sense, because the x values that would produce these volumes are actually getting closer and closer to infinity. X has a limitation. Let me go back to our picture, right? I can't cut out this size of a square. I'm limited by the 8 and the 11. So you'll notice that right here, there it is, that's at the point 4, 0, that's where the graph starts going below the x-axis, right? So those would be negative volumes. That wouldn't make any sense either. So really the only part of the domain that we're interested in would be from 0, that would be not cutting a square out, to 4 inches. That would be cutting the entire thing out. So we're limited to just that. So I'm really just looking at this part here, and this part does have a maximum. And it says that the maximum occurs at 1.525. That would be the dimension of the square. That would be in inches. But the volume is our y value, so that's really 60.013 inches cubed. So let's write that down. And we've answered the question. Let's move on to something that's a little bit more complicated. So question 2, you're designing a right circular cone-shaped box for a special toy. That's really just a cone with a height and a radius that meet at a right angle at the center of the circle. And we are given that 800 centimeters squared of cardboard is available. So what dimensions of the cone would give us the maximum or maximize the volume of this cone? So sounds very similar to the previous question, but now it has surface area that's also involved in it. So let's start with surface area of a cone. So surface area of a cone is the base, and notice it's set up here. Make sure to include the base of the cone so the box will completely enclose the toy. The base is a circle, so we have pi r squared. And then we have the lateral part of the surface area. That's called pi r L. And a reminder that L is this slant height right here. You know, while we're over here, let's remind ourselves how we could figure out what L is. We have a nice right triangle, so I'm just going to set up some Pythagorean theorem. So the height squared plus r squared equals L squared. So now we have a relationship between those three things. But I'm still keeping in the back of my mind, you know, what am I trying to figure out? This says we want the dimensions of the cone. So the dimensions of the cone would be what is R and H that would give us the max volume. Okay. We could also say the slant height, but if we knew R and H, we would automatically be able to find the slant height. So really, I just care about these two things. Okay. I haven't even written down volume yet. We might as well do that right here. The volume of the cone is a third of a cylinder. So it's a third pi r squared h. Okay, so we have 3 different things that we need to start playing around with. The last question, we graphed the volume and we found its maximum. So that still sounds like a really good plan, but if I type this into my calculator, the problem is that we have 2 variables here. And I can't do that. So I'm going to need to figure out what h is in terms of r, or what r is in terms of h. And I can do that, right? I have other equations that use those variables. Over here in surface area, we have r. We don't have h, and we also have l. And then over here, we do have h and r and l. So let's think about this. If I wanted to plug h equals something in terms of r in, I could take this equation, solve it for h, plug it in, but it's going to have r and l in it. So that's not going to fix the problem. Maybe this over here can help me because it is in terms of r and l. So I think we're going to take kind of 2 of equations here and substitute it into this volume. Okay, so kind of the big ideas laid out. Let's just kind of start with what's given and go from there. So I know that the surface area is going to be 800. That's 800 centimeters squared. That's the cardboard that's going to be used to make the box. That's the surface area. So here we have our surface area. We could solve this for L, come over here. L wouldn't exist anymore. It would just have R's, right? Because it would be solved with only the other variable left in here. and then I'd have h's and r's, which is exactly what we have here. So I think that now we have a more laid out plan. This is going to work well. So let's take this equation and let's solve for L. So to do that, I'm going to subtract the pi r squared and then divide both sides by pi r. So I have that L is 800 minus pi r squared over pi r. Great. Let's come over here, and I'm going to plug it in to L. So we have that h squared plus r squared is a lot of stuff in here, so let me just get all this down. The 800 minus pi r squared over pi r all squared. Okay, back to the big plan. Remember that we need to take this and solve it for either h or r. I'm going to go for h and then substitute it in here. So I want to get h by itself. So I'm going to do h squared equals this big thing squared, and just move that r squared over here, right? That got the h squared by itself. And then I have to take the square root. And normally when we take the square root, we like to put the plus or minus in front. That doesn't make sense in this problem because height couldn't be negative. But I did think about it, just so you know. So this nasty stuff is what h is. And now, you know what, I'm just going to erase this line so I can draw another line. And now I'm going to go into h. So the volume is 1/3 pi r squared times the square root of 800 minus pi r squared over pi r quantity squared minus r squared. Craziness. I don't need those parentheses, but I don't know. I think I'm more comfortable leaving them there. That's my volume. That's the thing that I need to find the maximum of, right? I want to find the max volume, but I want to know the dimensions. So before I even type this in the calculator, remember that the V is really like our Y, and the R is really like our X. So when we find a point and we see its Y value, that's telling us the volume. And when we see the X, that's really telling us the radius. So we're going to find the radius first, and then that's going to lead us to a height as well. Right? That's the real goal here. So let's go to the calculator. All right, so I set up our graph on Desmos. If you're using your graphing calculator and you're looking for an appropriate window, definitely think about restricting your x-axis from 0 to 10, just because it really wouldn't make sense to have a negative value. And even without seeing the maximum on the screen, I'm fairly certain that radius is going to be pretty small. And I just kind of followed the graph all the way up. It turned out to be in the 1500 range. And I have my maximum. So let's record those values. The x value, which we said was the radius, is 7.979, and that's centimeters. And if, not that this is part of our actual answer, but I am going to write it down just so we have a record of it. The max volume is going to be 1,504, approximately that amount of centimeters cubed. So the only thing we're really missing now is the height. So we need to take our radius, come over here, plug that in, and see if we can figure out our height. So the square root of 800 minus pi times the 7.979 squared all over pi times 7.979. But then this fraction has to get squared, and then we have to subtract the 7.979 squared. Oops. And that's all inside the square root. So then that has to get typed into the calculator. I have already done that on Wolfram Alpha. You can see here, I like using Wolfram Alpha because you can actually see. It translates it into the correct notation. So I have this result right here, so let's fill that in. So our height is going to be 195.838 centimeters. And that's exactly what we were looking for. Now, if I were taking a test, you know, if this was some type of high-stakes situation, I would actually figure out what this would produce as a volume, right? Plug into the volume equation and make sure that this is what we get, and check and make sure that the surface area is also 800. Obviously, there's lots of weird stuff going on here, lots of places to make mistakes. I may have even done it in the video. I hope not. I double-checked everything. But if I did, you can let me know. And I will see you all in class.